Hello everyone, this is Masumi Villeneuve from Department of Integrated Global Studies, School of Integrated Arts and Sciences. Today I'd like to invite you to the world of interface science. These are the topics that we are going to talk about today. Interface is the boundary between two spatial regions filled with different matters. Here is a piece of glass capillary filled with water and surrounded by air. In this slide, there are altogether three interfaces, namely an air-water interface, a water-glass interface, and a water-glass interface. Parallel to the interface, the force of interfacial tension acts. It is the force which tends to minimize surface area. Objects of a same volume can have different surface areas. Between a cube and a sphere, the sphere has less surface area. Thus, a round shape of a liquid is due to interfacial tension. I'm going to show you an experiment using Japanese 1 yen coins. 1 yen coin weighs 1 gram and its volume is 0.47 cubic centimeter. It is floating on the water surface, but if only the buoyancy were considered, the coins should sink into water. The reason it stays on the water surface is the surface tension acting along the edge of the coin, pulling it upwards. Surface tension is the term used instead of interfacial tension when one of the bodies in contact is a gas or a vapor. Coins were placed on the water surface one by one. As the number of coins increased, they started together and stayed close to one another in the hexagonal closest packing state. The coins move to one another because surface tension tends to minimize surface area between the coins. Although we seldom notice, our daily lives are full of substances and processes under the influence of interfacial tension and surface tension. Now, I would like to address some features of substances in which interfacial tension plays significant roles. Such substances are called colloids. A colloid is a mixture in which particles of one substance are dispersed through a second substance. The particles of the first substance make up dispersed phase, and substance that they are mixed into is the dispersing medium or the dispersing phase. The general size of colloid particles encompasses about 10 to the minus power of 9 to 10 to the minus power of 5 meters. For comparison, the average diameter of a human hair is around 50 micrometer. In this slide, the relationship between the relative intensity and the wavelength of light from the sun is shown. And as you can see in this figure, large colloidal particles have dimensions on the order of the wavelength of visible light. So they interfere with visible light. These are aqueous solution of surfactant, a kind of soap, alcohol, and sugar. All the samples have same ingredients, which are colorless per se, but in different concentrations, resulting in different colloid sizes. They have structures of sizes optimum to interfere with visible light of a particular wavelength. Such color is called structural color. It is vivid and stable as long as the colloidal structure keeps existing. In fact, these samples have been in my laboratory for more than 20 years. We see other examples of colloid in this slide. Fog and smoke are colloids called aerosol, in which dispersing phase is gas. And dairy, milk, and cream are emulsion. In emulsion, both the dispersing medium and the dispersing particles are liquids. Now, let us think about the volume and the surface area of a body. If we divide this cube into small pieces, the total volume will not change, but the total surface area will increase. And the smaller the pieces are, the larger the surface area becomes. The surface area of a cube that has 1 centimeter each side is 6 square centimeters. This cube is divided into 1,000 cubes by slicing each size into 10 pieces. The total surface area will be 60 square centimeters. If the pieces are of nanometer size, calculation is done in the same manner, and we get 6,000 square meters. This is 10 million fold of the original surface area. Properties of such colloidal mixtures are primarily determined by the chemical and physical properties of medium, the dispersing medium, and the dispersed particles. Moreover, the interfacial tension between the dispersing medium and the dispersed particle influences colloid properties. These are photographs from my studies on swelling mechanism of gluten-free, additive-free rice bread batter. In the picture on the left-hand side, the bread was successfully baked to give a soft and light texture. However, in the picture on the right-hand side, foams inside the bread collapsed. The chemical compositions of the two samples are the same. What makes the difference is surface tension. Before going into details of the swelling mechanism, I want to talk about the origin of surface tension in liquids and how it is changed. Surface tension is the attractive force in liquids that pulls surface molecules into the rest of the liquid, minimizing the surface area. In a liquid, there are two types of molecules: those that are on the surface, exterior, and those that are inside the liquid, interior. The interior molecules are attracted to all the molecules around them, while the exterior molecules is attracted to the other molecules in the surface and to the molecules below the surface. And because of this, molecules inside the interior molecules, the energetic state of the interior molecule is much lower than the energetic state of the molecules on the surface. Because of this, the molecules try to maintain a minimum surface area possible thus allowing more molecules to have lower energy state. This is the origin of the surface tension in liquids. So the surface tension is the excess free energy per area. The stronger the intermolecular interaction is, the higher the surface tension becomes. Here, values of surface tension at 25 degrees Celsius for various liquids are listed. Between water molecules, hydrogen bonding is formed, which is fairly strong intermolecular interactions. So water has the highest surface tension among the non-metal liquids. On the other hand, between hexane molecules, that is a linear alkane consisting of 6 carbons and 14 hydrogen atoms, van der Waals force is the intermolecular force that is acting between the molecules, which is relatively weak force. So it has a very small value for the surface tension. Mercury is the only metal that can exist as liquid under atmospheric pressure and ambient temperature. The metal atoms, the bonding between the metal atoms are quite different from those between molecules. Metal atoms are rather sharing and exchanging electrons, so it is a very strong interaction, and hence the mercury has a very high surface tension value. When a substance comprised of molecules having both a hydrophobic group and a hydrophilic group in one molecule is dissolved in water, it is condensed at the water-air interface. Because surface tension of hydrocarbon is much lower than surface tension of water, the water-air interface is replaced by the hydrocarbon-air interface, and consequently, the surface tension of the surfactant solution decreases. This thin layer formed at the water-air interface is called a monomolecular film, and such a substance prone to be adsorbed at the interface is called surfactant. The depth of the interfacial domain is of nanoscopic scale. However, roles of interface is non-trivial in colloidal mixtures. Now let's talk about the rice bread. Okay, rice is the major staple food across Asia, and in Japan it has been the most important agricultural product. Nowadays, the annual consumption of rice is 61 kilograms per person, which is about half the amount used to be eaten 50 years ago. On the other hand, wide prevalence of wheat allergy and celiac disease has led to a growing demand for gluten-free foods. Rice is less allergenic than wheat, and it is considered a suitable substitute for wheat. The swelling of bread dough is due to gluten. It forms a branched fibers tangled to develop network structures as the dough is kneaded. Carbon dioxide gas produced by yeast is confined in the network to increase the volume of the dough. Gluten is not only the inflating agent, but it also gives nice texture and flavor to bread. However, at the same time, it is the major cause of the diseases. So these photographs show raw rice batter and wheat dough. Both the batter and the dough consist of 50 weight percent flour and 50 weight percent water. And the wheat dough appears cohesive and elastic, which is the effect of gluten network. And the rice batter looks rather fluid. So the conventional resolution, I mean the tips for baking a rice bread has been addition of gums or hydroxy propyl methylcellulose, which is a semi-synthetic dietary polymer based on cellulose. But recently, a new way to bake a rice bread without any such thickeners. And as you can see the difference in the appearance, the mechanism that occurs in the process of rice bread making must be different from the process occurring in the wheat bread making. So not any rice flour is suitable for additive-free rice bread. The photographs show surfaces of bubbles in portions of fermented batter before baking. They were observed with a scanning electron microscope, SEM. The SEM uses a focused beam of high energy electrons to generate a variety of signals at the surface of solid specimen. SEM can magnify objects much larger than an optical microscope can do. So we can get detailed information on the surface morphology. So the pictures in panel B shows the surface morphology of the bubbles in the batter. And in the sample in which rice flour, which is suitable for bread making, shows a stone wall-like structure. And well, this is the micrographs observing the same spot with different magnification. So you can see the edge of the dissected bubbles remain sharp in the sample with good rice flour. But in this sample, where rice flour, which is not so suitable for bread making, is contained, the edge of the bubble, dissected bubble, looks smooth, unlike this picture. And the magnified picture shows that a part of the bubble surface is smeared, somehow smeared. So in this graph, the vertical axis is the specific volume of a loaf of bread, and the horizontal axis is the extent of starch damage. The specific volume of a substance is the volume of 1 gram of the substance occupies. You see rice flour of low extent of starch damage makes bread with high specific volume. And the value, the 4 cubic centimeter per gram, is comparable to the traditional wheat bread. By the way, what is the degree of starch damage? It is defined as the percentage of starch that is subject to enzymatic hydrolysis. And from all the samples, sample number 5 and number 7 were chosen to test their properties. The chemical compositions of the two samples are practically the same. The starch is about 81%, protein is about 6%, lipid 1%, and ash 0.2 to 3%. And number 5 and number 7 flour was respectively dispersed in water, and the surface tension of the water was measured. When rice flour is dispersed in water, starch granules that comprise rice flour are scattered. Starch granules of rice have dimensions of 2 to 8 micrometers. This is the smallest dimension among starch of plants consumed by human beings, such as potatoes, cassava, wheat, corn, and so on. Additionally, the shape of granules is polygonal. The vertical axis is the surface tension, and the horizontal axis is the mass of flour dispersed in 100 grams of water solution, dispersed solution. Number 5, which is suitable for bread, lowers the surface tension of water definitely more effectively than number 7 does, which cannot make soft bread. The ability to lower surface tension of water is technically called surface activity. The surface activity of number 5 is as strong as that of common surfactants. So this is the schematic diagram of an idea we got from the surface tension measurements. We confirmed this hypothesis by performing other experiments. So we proposed that a mechanism behind our new food technology for producing soft and bulky bread, rice bread, is stabilization of carbon dioxide gas bubble in the batter due to surface activity of rice starch granules. In the rice flour dispersed solution, starch granules play a similar role as surfactants. The degree of starch damage of rice flour, the morphology of the bubble surface in the batter, and the surface tension values of the rice flour dispersed water are all strongly correlated. Our ongoing project is to clarify the cause of difference in the surface activity of rice flour of different degrees of starch damage. So to control colloidal properties or to conduct researches on colloids, knowing interfacial tension is very important. How can we measure interfacial tension? There are many ways to do it. Now I'm going to show you some of them. The first is the drop weight method. You measure the weight of falling droplets. While a droplet is hanging on an end of a glass tube, two forces are in balance. One is the surface tension acting along the edge of a glass tube, supporting the droplet. And the other is the gravity pulling the droplet downwards. A much simpler and easier method, but not so accurate, is using a Stellar Monometer. This is a glass tube filled with a liquid sample. The principle of surface tension determination is the same as drop weight method. Instead of measuring the weight of falling droplet, you count the number of droplets while you let the liquid of a given volume flow out of the glass tube. The last one is a method based on image analysis. You take a picture of a droplet of a liquid. If the only force acting on the droplet is the surface tension, the droplet will be a perfect sphere. However, if the force of gravity is present, which is always the case on the Earth, the sphere will be deformed from a perfect sphere. So the extent of deformation is determined by the magnitude of surface tension. So by analyzing the contour of the droplet, the surface tension can be estimated. Let's change the subject a little. We all know that there are three states of matter. For example, carbon dioxide transforms from solid to gas under atmospheric pressure. At room temperature, it transforms from gas to liquid, then from liquid to solid when the pressure is raised. Similarly, matter in interfacial region takes various states. The monomolecular film can take a gaseous state. It undergoes a phase transition and takes a liquid expanded state. It could also be in a condensed state, depending on the temperature, pressure, and surfactant concentration of the solution phase. By changing states of the interface between the dispersed particles and the dispersing medium of a colloid mixture, we can change stability of an emulsion or change a colloid from one type to another. Homemade butter is a good example. Dairy cream is an emulsion in which liquid colloid particle made of milk fat and protein are dispersed in liquid water. It looks white and opaque because colloidal particles are about 2 micrometers and they scatter visible light. Pour some cold fresh cream in a jar, close the lid, and keep shaking the jar for 15 minutes. The fresh cream will suddenly turn into butter. Cream is an oil in water emulsion. Butter is a water in oil emulsion. Lowering the temperature changed the interfacial state between oil phase and water phase, and that leads to phase inversion. There are more interesting phenomena inherently associated with interfacial interactions. To wrap up my talk today, the concept of interface and colloid were introduced. The origin of surface tension in liquids was explained. Then some results from my studies on the swelling mechanism of gluten-free rice bread were demonstrated. A few methods for measuring surface tension were described. If you're a high school student, a Stellar Monometer might perhaps be useful in your scientific activity at school. And I talked about cream and butter from a perspective of interface science. Let me finalize my talk with this slide showing areas of human activity where colloid and interfacial interaction plays significant roles. Thank you for your attention.